Simon's lecture series this semester. It's a great pleasure to introduce Jean-Pierre who will be giving lecture series, and the first lecture is titled Holomorphic Morse, Inequalities, and the Green Griffiths conjecture.
Thank you very much for the introduction. So I'm very glad to be here and feel very honored to give James Simon's lectures on this week. So I will try to explain some basic results about holomorphic Morse inequalities and applications to algebraic geometry, especially a recent result concerning the Green Griffiths conjecture, which is a conjecture about the behavior of holomorphic curves drawn in projective algebraic varieties of general type. So let me start with very basic definitions. So X throughout the talk will be a compact complex manifold. N as dimension. And we consider L over X a holomorphic line bundle. Then, of course, you have a d-bar operator. And you can use the d-bar operator to compute cohomology. So you look, for instance, at PQ forms, and you consider HPQ XL, the PQ d-bar cohomology group. It's enough to consider P equal to 0, actually. It's well known by using sheaf theory that this is the same as the cohomology into the coherent sheaf of sections of the line bundle M. Using, for instance, Czech cohomology or whatever. Okay, so we are interested in understanding better general properties of this, especially the asymptotic cohomology. So I will introduce the asymptotic cohomology groups. Or group dimensions, functions. So by definition, I look at H hat Q XL, and this is the lim sup as k goes to infinity of, well, you renormalize by n factorial for some reason, divided by k to the n times the dimension of x into the kth tensor power of L. So here small h means just dimension. So h, small hq of xl means dimension of those groups. Okay, and now you want to understand the asymptotics as k goes to infinity of the growth of the cohomology groups. Of course, if you look at the Euler characteristic, things become much simpler. So the Euler characteristic is just by definition the alternate sum of dimensions. And then it is well known that if you look at the case power here, then you get a polynomial, which is a so-called Hilbert polynomial. It can be computed by the Riemann-Roch formula. So by Riemann-Roch, it's equal to the integral over x of the Chern character, which in that case is just exponential k times C1 of L multiplied by the Todd class Tx. You take the n part to integrate, and actually you get a polynomial such that the leading term is k to the n over n factorial times the first Chern class of L raised to power n plus lower order terms, which can be computed in terms of the Chern classes of L and X. The drawback of this formula, although it is very strong and very useful, is that it doesn't give any information on the individual homology groups. You only have information on the determinant sum, which is definitely useful, but not complete information. And therefore, you would like to know more. As it turns out, there is an analog in the holomorphic case of the Morse inequalities. So here in the land of John Miller, I will not explain to you that Morse inequalities are very useful. So they are very useful in the differentiable category, but they are equally useful in the holomorphic category. So unfortunately, in the holomorphic category, the homomorphic Morse inequalities hold true only asymptotically. You don't have, in the real case, you look at the Morse function, you look at the critical points, you look at the indices of the critical points, and then you know that the alternate sum of the theorem, or the Betti numbers, let me denote them by HQ, they are HQ in the sense of theorem here. And then you have an inequality in terms of the number of critical points. So you look at the critical points of various indices, and then you have such an inequality in terms of the number of critical points of any index. In the complex situation, you have an analog, but you don't have the concept of isolated critical points. So this is replaced by something different, which is obtained by computing curvature. So let me recall concept of curvature. Of course, it's well known to many of you. So suppose you pick the Hermitian metric on L, which I will suppose to be smooth. And locally, you can trivialize the bundle.
Different little h.
Sorry?
You already used the letter little h. It's a different one. So there's no
H, yes, H and H, well.
okay. As long as people
there are no indices to that H. That is the difference. Okay. But I will not make use of much of that. Okay, so locally, you pick a point here, you identify a point to a complex number, and then the metric is just defined as a corresponding complex number multiplied by some weight, which is convenient to write as exponential minus p. And then you can define, you can take this as a definition, although it's better to use a connection, of course, but I will not explain that. You take I over 2 pi times dd bar of the weight phi here. And this does not depend on the choice of the trivialization, and gives a 1-1 form, which is a real 1-1 form. It's of type 1-1. And then the Chern class is just the cohomology class of this form of type 1. C1 of L can be taken to be just the cohomology class of the curvature form for any choice of the Hermitian metric. Okay. Now I'm introduce the analog of the Morse sums. They are Morse integrals. So the Q's Morse integral is the integral over a set which I will denote by L, H, Q of the curvature form raised to maximum power n with correct sign. And here, so you look at x, you look at any point x at the signature of the curvature form at point x. So you suddenly have a set where one of the eigenvalues is 0. So you have the, here this is a set where determinant is 0, so this is degenerate. And then you have some kind of chambers where you have signature, so n positive eigenvalues. So this is index 0, index 1, index 2, etc., index q. So index q, I mean n minus q positive eigenvalues and q negative eigenvalues. So in contrast with the real case, these are open sets, which are real analytic if you take a real analytic matrix, say. Smooth. If it's smooth, then it's just random open sets. Okay, and then you have to introduce the analog of the Morse partial sums here. So you introduce what I will denote by H hat. So it's the asymptotic cohomology. But now you take the lim sup as k tends to infinity of n factorial over k to the n times the alternate sum of the Dolbeault d-bar cohomology groups. Go to H0. Okay, and then the theorem is as follows. So this is the main result which I got very long ago, 1985. That this asymptotic cohomology is controlled for any smooth Hermitian structure R. The asymptotic cohomology is controlled by the Morse integral. But then you should take the alternate sum. Of course, you should take IQ minus IQ minus 1. Which is the same as the integral over a set which I will denote by XLH at most Q, which means that you take the union of the chambers where you have index 0, 1, etc. up to Q. So this is the basic theorem. Let me. So in case you have Q equal to dimension, this is the complete sum, so it's the Euler characteristic. And then what you get is the integral over the whole of x, because of course the integral on the degenerate part is 0. So it's the complete integral, so it's up to the sign, it's the leading coefficient of the Hilbert polynomial. And the normalization by n factorial is just to compensate here. It's just the inverse of this growth.
And the lower order terms?
In this way, you don't have lower order terms. If you go back to the cohomology groups, it means that you have an error term which is negligible with respect to k to the n. So you have lower order, although you don't know as precisely as in the Hilbert polynomial that this would be a gross k to the n minus 1. Depending on the behavior of the curvature, it could be worse. And depending how you have degenerations here, it's rather subtle. Okay, so let me give you a hint of how this is proved. Although the details are not so short. So it's some kind of variation of the Atiyah-Bott-Fatoli method. So you have a localization procedure. And also you combine this with Edward Wheaton's technique for proving the ordinary Morse inequalities by some heat kernel technique. So let me give you just a few ideas. So basic thing is to introduce, of course, the... Sorry?
How should we think about the slim soup? Because it could be negative, or you could have something that is the lim soup, but most of the action takes place far before the soup, right?
Already, from the definition, it's not completely clear that the lim soup would be finite. Of course, the theorem tells you that this lim soup is finite, because it's controlled by something which is computable by curvature. And you can show that the lim soup cannot be minus infinity. You can show that the lim soup is a real number.
But you could have lim soup here, but most of the action is here. So what kind of information do you have in that case?
Well, one of the difficulties is we still don't know at this point in any dimension that the lim soup is actually limit. The expectation is that all terms here have limits. That the lim soup is actually a limit, and that each individual term in the sum has a limit. But this is hard. This is one of the conjectures. Okay. I will come to this. So, idea of proof. So, you look at L to the power k. You put, of course, as a metric, the case tensor power given dimension metric. And then you compute the complex Laplace operator, which is d bar, but d bar, I will denote by d bar k here. It's the d bar acting on this bundle. As usual, you take d bar star plus d bar star d bar. And then it's well known that cohomology is given by the harmonic form, so by the zero eigenvalue of this.
Now you're on Taylor. Now you're on Taylor.
I don't assume, no, we don't need Taylor. Don't need Taylor. Any compact complex manifold. Oh, yes, I agree that you have to compute the dual, so here you take an auxiliary Hermitian structure on X to compute the adjoint here. You need that. Take auxiliary Hermitian metric, but you don't need Taylor. So this is a metric on Tx, the tangent bundle. Okay, so you compute the adjoint, and then you look at the harmonic sections, and of course you have that HQ of X into L by Hodge theory is isomorphic to the harmonic forms for this Laplace operator with values in L to the K. And now you use Wheaton's idea. So the idea used by Witten is to replace computation of cohomology with infinite dimensional spaces by finite dimensional spaces. And these finite dimensional spaces are precisely eigenspaces of the Laplace operator. So you look, let me introduce E, Q, lambda. This is the sum, or maybe at most lambda. This is the sum of eigenspaces. It's an elliptic operator, so the eigenspaces are finite dimensional. So you look at the sum of eigenspaces of this Laplace operator, but you renormalize for some reason by 1 over k. I will explain later. With eigenvalues at most lambda. And then it turns out that, of course, del bar commutes with the Laplace operator. Just by definition. And therefore, this makes a complex of finite dimensional spaces, because the eigenspaces are mapped by d bar on eigenspaces in degree 1 more. So you get a complex. The cohomology of this complex is again given by the zero eigenvalue, by the harmonic forms. Of course, elementary application of linear algebra shows that the alternate sum of cohomology groups is less than the alternate sum of dimensions of those finite dimensional spaces. So you only have to estimate the dimensions of those equal at most lambda. And it turns out that you can compute. So, assertion K, one can compute limit, and it's actually limit as k tends to infinity of 1 over k to the n times the dimension of those things. Of course, it still depends on the k. Maybe I should put a k. So I will not give details, neither I will give a formula, but I will tell you why this is computable. This is very easy. Because if you compute the L2 product, this is of course the norm of del bar square plus d bar star square. And when you compute in coordinates, you have something like this. So you have derivatives. And then you have the connection matrix. But the connection matrix gets multiplied by k. With some sum with respect to the derivative. And then you have a curvature, but the curvature gets multiplied also by k. So you have some potential here, plus k, v, it's a Hermitian operator, and then you integrate. But now this is a reason why I renormalized. So I put 1 over k. Okay, so you have 1 over k here, and now this k disappears. And now you zoom on the horizon. So you are going to make a change of coordinates. Yeah, actually, you trivialize the coordinates and you approximate the linear part. So you can always achieve that a at some point 0 is 0. So essentially you can replace by, well, okay, it's a of x, but you can change coordinates so that at any given point the connection matrix is 0. Okay, and then you change coordinates and you put capital Xi is equal to square root of k times xi. So you zoom by this factor square root of k. And then you see that this sum becomes sum over I of du over d capital Xi plus, now this is 0, so you divide by square root of k, and then you obtain the derivative essentially of a prime at 0. And here, because you zoom, you get value of v at 0. So intuitively, you are zooming, so you are dividing the variety in small cubes. And the size here of the cubes is roughly 1 over square root of k. And you are zooming and looking on each small cube the behavior of the object. And of course, everything becomes with constant coefficient, because when you zoom, I mean, the variation becomes very small on a cube. And you can of course compute completely the spectrum of the corresponding Laplace operators for constant metrics with constant curvature and constant potential or whatever. And this is completely computable. So the local asymptotics on each cube is known, and then you sum up for the cube. You have some partition of unity argument, but then you can estimate the growth of this. The wavelength, somehow the wavelength of the phenomenon is 1 over square root of k. And you are looking at waves such that the length wave is 1 over square root of k. And this is the explanation. Okay. So now, it's interesting to understand a little bit better what are these functions. So, first observation is that you can extend to the well, you would like to extend to the Néron-Séveri vector space. So you define the Néron-Séveri real vector space of X to be the real subspace, real vector subspace of H11 of XR. So if you insist on looking at a non-Kerr manifold, you should not look at the ordinary Hodge group, but you should look at the Vodcher cohomology. So here you look at the D-bar cohomology. But this is absolutely okay here because the C1 of L is defined by a DD bar. So the C1 of L makes sense in this enriched theory. Of course, in the Keller case, it's just the usual H11. You take the real subspace, which is generated by integral classes. And integral classes of type 1, of type 1. My standard theorem of Weil, this is the same as the Chern classes of holomorphic line bundles. So this is the same as the vector span over real numbers of the Chern classes. Okay. And now you pick an element in this vector subspace. And now the question is, you would like to define a function on this. And then, well, you can do this. HQ hat of X alpha. You are going to take this. You are going to take the lim sup over all pairs LK in such a way that 1 over K converges to alpha. here you have a space with integer points, but of course if you extend to rationals, it becomes dense in the real vector subspace, and then you can converge to a real class. And then you take the lim sup of the HQ of XL in these conditions. So maybe I should put LK if you. So you take sequences of line bundles in such a way that 1 over k, C1 of LK converges to alpha, and you take these lim sups. It's not completely clear that this will coincide with this, but in fact it is true on a smaller subspace. In general, it would be a conjecture. So maybe I can state this as a conjecture. So the HQ, which I defined earlier, actually is purely numerical and depends only on the Furtian class C1 of L. Of course, to prove this, you have to prove some kind of stability that these groups, sorry, it's H, I forgot the n factorial over k to b. You have to prove some stability. This definition is by looking only at powers. But here you look somehow at all possible rational approximations. So you have things which are nearby the multiples, and not just the multiples. So here you, of course, with this definition, you have an inequality which is obvious, but the equality is not true. But this is true, at least on the subspace. So the theorem, it's not very hard to prove. So I will introduce the divisorial Néron-Severi space. So instead of picking all line bundles, you pick only the effective divisors. So take the real span, D are effective divisors. Of course, if X is projective algebraic, this is the same, because any line bundle has rational sections. So, the projective algebraic case is the same. So this is equal to the usual Néron-Severi in the projective algebraic case. In general, it might be different. Then you do have equality on this smaller subspace, and in particular, the conjecture is okay for projective varieties. Then?
I forgot what effective divisor means.
With positive coefficients.
What?
Divisor with positive coefficients. Okay. Well, actually, I forget because I take real combinations. So I take integral divisors. Then equality holds true, so it means that asymptotic cohomology does not depend on the isomorphism class of the bundle, but depends only on the numerical class of the bundle. So it's a numerical invariant rather than a algebraic invariant. Maybe I should have denoted by a different symbol. Moreover, Moreover, if you look at this map, so the asymptotic cohomology function, so now it's a map which is defined on a finite dimensional vector space. It's defined on, you look at only on the divisorial part. So you go into the positive real numbers. Well, this map is homogeneous and locally Lipschitz continuous. So it satisfies. So homogeneity is obvious. So if you multiply by a factor, okay, well, you can approximate the real numbers by rational numbers. So if you raise L to a multiple, then this multiple gets multiplied, gets raised to power n. So what you get is this homogeneity. And now you have some kind of continuity. If you compare some Lipschitz continuity, this will be less than a constant times norm of alpha minus beta times norm of alpha plus beta to the n minus 1. With respect to any norm, it's a finite dimensional vector space, so all norms are equivalent. So you pick any norm on this finite dimensional vector space. And then you see that the cohomology somehow behaves continuously when you vary the line variance. So let me give you a rough idea of how this is proved. This is not very difficult. Actually, these ideas were already considered by algebraic geometers a few years ago, although not in this generality. So all these concepts in the algebraic case were considered by Alex Couronja. And papers also by Rod Blazesfeld, Lawrence Ein, Sean Ustaza.
So alpha and beta are in the cohomology?
So here this property is in this in there.
What does this norm mean?
You are here on a finite dimensional vector space. So you pick any norm, and then of course the constant will become the choice of the norm.
Oh, the constant.
That is a constant. So the idea is quite simple, actually. So suppose you have two line bundles which differ by a small amount. If they differ by a small amount, it means that they differ by a small Q divisor. So epsilon d, it's a small Q divisor. Well, if you are, I use only one, but if you are in a finite dimensional vector space, they would be generated by some basis, d1, capital N, and then you would take a linear combination of several members. Let me take only one to simplify notation. Actually, it would be some kind of, you would generate everything as a class by taking small sums to the basis. Okay, and then you raise to some multiple. Of course, you are going to take a multiple so that you eliminate denominators.
You want to say the line bundles themselves, or that there are some multiples of their term classes that provide something small? Yeah, since you can't.
Well, actually, you take a Q. You are going to prove continuity. A function which is defined over a dense subset extends if it's uniformly continuous.
Right, you're starting with integer classes, and elemental prime, of course, are integer classes rather than rational. So I just wanted to say.
So I'm going to take rational classes. You are going to prove this on rational classes, and prove this inequality, and then you prove that it is uniformly continuous, and therefore you have a continuous extension to the real classes.
So L and L prime are actually roots of line bundle.
So in this proof, you should think of L and L prime as Q-line bundles, differing by a small Q divisor. Okay? But then, since anyway you compute asymptotic cohomology, you are ready to take large multiples, and therefore you don't care that they are Q-line bundles, because you can take a power which is an integral line bundle. So after you raise to a power, you can assume that these are integral line bundle divisors. And then you can, of course, take the positive part and the negative part, and then by comparing, you can assume that the divisor is either positive or negative. Assume it's, say, negative. May consider the negative case. D now is positive. But then, of course, you have an exact sequence. And here you look at the restriction of L to the k to some subscheme, which is the subscheme defined by the quotient of OX by OX of minus k epsilon d. And then you want, this is the L prime. And you want to compare cohomology of this and cohomology of this. So by the exact sequence, you have to look at those groups. But now those groups, they live in the support of a scheme, in a scheme which is supported on D, so it's a dimension 1 less. So you still have to compute the multiplicities, but essentially by induction and dimension, the cohomology that comes from the term on the right is small. Because the epsilon is small, and therefore the multiplicities of the scheme are small, and then you control by Riemann-Roch. So you have a dimension which gives you k to the n minus 1, and then you multiply by multiplicity, which is epsilon k. So you have epsilon k to the n by Riemann-Roch, and therefore you have shown the continuity. So the continuity comes from this.
That doesn't give you a uniform constant, does it?
Sorry?
Does that give you one constant for every, a uniform constant?
The constant, to have a uniform constant, you have to work a little bit more. But it comes from the fact that you are in a finite dimensional vector space, so all your divisors can be generated by a finite family of divisors, and then you have to control uniformly for all these divisors. It's not very hard. Okay, so now that we understand a little bit more the asymptotic cohomology, one would like to relate the asymptotic cohomology to the Morse integrals. And now let us make a bold conjecture. Maybe optimistic. That the asymptotic cohomology of any holomorphic line bundle is actually obtained by the infimum of the Morse integrals. So you take all possible smooth metrics and then you compute the Morse integral with respect to the curvature of that metric, and take the infimum of all. You know that this is less by the Morse inequalities. And you expect that this is optimal. Namely, that if you take the infimum of all smooth metrics on L, then you will get equality. And the same for the alternate sums. So if you take the lim sup of the alternate sums, then this will be the infimum over all smooth metrics. And here you take the integral over open sets which are index 0, 1 up to q. And in the package of the conjecture, also you add that all lim sups are limits.
If you were to make the analogous conjecture in the real case, it would be false, right? It would be like saying that you could always have a perfect Morse function up here.
Yeah, exactly. I was going to say that in the real case, you would expect perfect Morse functions. Perfect Morse function that realize the cohomology. Here you have some hope that you take an infimum over a continuous set. As we will check very soon, actually both sides are, for instance, birational invariants, Holomorphic invariants. So you can allow blow-ups and such things, and it still works. And you can also allow things which are negligible. So this is what maybe is missing in the real case, is that you have a continuous problem. A discrete problem is harder. So maybe conjecture could be true. So this will be my next observation. So I still have one here. So observation. So of course the asymptotic cohomology here is a bimorphic invariant. So if you have two manifolds, and then you perform a sequence of blowups, so you have a modification. And then you start with a line bundle here, and then you take the pullback. Then the asymptotic cohomology of this and the asymptotic cohomology of L are equal. The reason is that you can use the Leray spectral sequence. So you are computing the direct images of the Leray spectral sequence, but all this is supported in the exceptional set. Because the exceptional set is of codimension 1, the growth of the powers occurs in dimension 1 less. So what happens on the exceptional locus counts at most for k to the n minus 1. Because this is cohomology of a line bundle on something which is of lower dimension. So for this reason, you are counting volumes. So you could analytically, you could think of that as saying that, well, you modify the curvature on the set of measure 0, so you don't modify the intervals. You are counting volumes, there are intervals. So if you blow up the manifold, you don't change the global volume. Okay. So this is a bimorphic invariant. It's a slightly more subtle argument to show that the Morse intervals are also bimorphically invariant. The infimum. I don't write for the second case, but it's also true. Of course, in the real case, it's not as well behaved, because if you blow up, you suddenly modify the Betti numbers. You are counting something which is not as stable as the volumes. The reason is that, well, in one direction it's clear. If you have a metric here, which is smooth, you can take the pullback, and then you get the smooth metric upstairs. So you have more metrics upstairs than you have downstairs. So certainly the infimum can only decrease when you blow up. And in the other direction, if you start from a metric here, of course it's a metric of a bundle which is trivial on the exceptional divisors. Well, if you blow up a point. So what you want to do is to push forward the metric. But of course, if you do this, you don't get a smooth metric. You get a metric which should be viewed as a singular metric downstairs. So you have to regularize this metric. And it turns out that by elementary techniques of plausible harmonic functions, so somehow on the exceptional divisor, the metric may vary. So you have a metric which is widely behaved on the points which you blow up. But then in those points, you patch the metric, which is something that you know already, which is smooth. You take a supremum. So you cut the metric here. So you modify the metric on a very small set, and because you integrate anyway, you can make this difference very small. So it's a regularization technique. It's not very hard.
How does Pierre subharmonicity enter here? There's no assumption on any positivity.
Okay. If you have two metrics, H1, which is given in terms of a fixed metric by some weight, P1, and H2, which is given by a weight P2. The standard way of patching plausible harmonic functions is to replace by max of P1, P2. So if you have a function which is badly behaved somewhere, so you have a function which oscillates a lot, and then you have another one which is smooth, you are going to add some pole here to make the one which is badly behaved smaller than the one which is well behaved. And then when you take the maximum, this bad behavior has been pushed down to -infinity, and when you take the max, you kill it. So it's a standard procedure for plausible harmonic functions. There are only quasi-plausible harmonic functions. Just matter of technique. Okay, and now I can state two theorems. So theorem 1, the conjecture, the optimistic conjecture, is okay for Q equals 0. So in that case, it's called the volume. So the volume of a line bundle is just the growth, the asymptotic growth of the section. So it's just h hat 0 of xl, and this is indeed equal to the infimum over all smooth metrics of the Morse sums on the index 0 set. And theorem 2, the full conjecture is okay in small dimension. So it's true, of course, in dimension 1. Well, in dimension 1, any line bundle can be taken to be a constant curvature, because you solve a Laplace equation. So it's the first Chern class is just a number on a curve, and then making the curvature constant is just a matter of solving a linear Laplace operator. So any line bundle on a curve can be taken to have constant curvature with respect to any given Riemannian metric, or Hermitian metric. And therefore, everything is trivial for curves. But for surfaces, it's non-trivial. That's still true. So conjecture, theoretic conjecture is true for dimension. At most 2. And the lim subs are limits in that case.
So does that follow from theorem 2 just by using the index theorem and the fact that the zeros of the second cohomology, you can interpret those in terms of 8 zeros?
Yes. Let me, well, I probably won't have much time to explain more details. The talk is supposed to be 1 hour, I guess. So I have 2 minutes. Okay. First, of course, you have Serre duality. Namely that h hat q of xl is the same as h hat n minus q of x l minus 1. With Serre duality, you have kx, but since you raise to multiples, the kx is negligible with respect to large multiples. Well, it may be true only in the projective case, where I forgot an x projective surface. And here, x projective as well. I cannot prove in general.
Yeah, but it would also be not L minus 1, but L minus 1 tensor to canonical 1.
No,
It's k times L.
no, because
Oh, it's asymptotic. Oh, I see. So
it's the asymptotic homology, so you don't care about constants. But because I'm claiming that the theorem is only in the projective case, the canonical is always divisorial. It would not be true that on a general compact complex manifold. You don't know that the canonical is divisorial. But because you assume it's projective, the canonical is divisorial, and therefore it's true. You still need this tricky statement. Okay. And then, of course, if you replace L by n minus 1, it means that you just change signs in the curvature. And therefore, the Q index set becomes the n minus Q index set when you reverse. So the intervals are reversed as well. And therefore, the theorem is also true for Q equal dimension. So this means that in the surface case, you are in good shape, because you know for 0, by Serre duality, you know for 2, and then you have Riemann-Roch, which gives the alternate sum of the 3 terms. So you still have control of H1. So this is why somehow you only have to prove theorem 1. You can prove theorem 1, and you will easily deduce for surfaces. But now it's still a challenge to prove for the volume. So unfortunately, I think I will not have much time except to say some advertisement for another work. So in that case, you have to prove it only when the volume is strictly positive. If the volume is 0, well, you make a different argument. So assume that the volume is strictly positive. It means that the bundle is big. But big means that after you perform a blow-up, you have approximate Zariski decomposition. So you can decompose the big part into ample plus exceptional part. Because you have invariance by modification, you are somehow reduced to proving in the ample case. And in the ample case, it's not that difficult. And then you have to understand somehow the interplay between the ample part and the exceptional part. And this interplay, well, a priori is not easy, but is solved by a paper I wrote with on the structure of the positive codes. So you have to know something about the geometry of code of positive divisors and arbitrary projective varieties. Using this, you have enough information on the connection between the ample part and the fixed part of the given model to understand what is missing. So this is roughly the slide. So I'm already over time, so I'll stop here.
So another laboratory to check this in is if you suppose that there's only one chamber. So suppose that the curvature is always a fixed signature on the manifold. There's some theorem that will say that the cohomology is sort of concentrated in one dimension.
That direction is easy.
Yeah, so
That direction is precisely the most important. The conjecture is the other direction, which you can call actually the paper. The name of the paper is converse to the undiluting Carnot theorem. Suppose that you know something on cohomology. Suppose that the cohomology is concentrated in the Q. Then you would like somehow to produce the metric such that the curvature only has points of index Q, or at least not so much of points of indices that are different from Q. You could still allow epsilon and go to epsilon equals 0 by taking the integral. So it's not absolutely perfect, but you want somehow to be able to reconstruct the signature of the curvature in terms of the knowledge of the asymptotics of the common groups. Actually, this is true for surfaces, so it's not completely hopeless. But in higher dimension, it looks hard. We would need a much deeper understanding of the result I just mentioned at the end on the structure of the positive codes. A lot of things that are still mysterious at this point. So I don't know.
So you started out by wanting to estimate in a fixed dimension, a fixed Q. So these partial sums get you a fixed dimension by induction. So you just estimate these Morse inequalities involve partial order differences, right?
Mm-hmm. Yep.
So the idea is if you know each one of those, then you know you start subtracting.
If you know that there are really limits and not.
Yeah, if you know that there are limits, then of course, yes, you are in good shape. Of course, it's sometimes hard to convert inequalities into equalities, but at least you have control on the individual terms. So in the next two talks, especially the last talk, the third talk, I will show you in a very concrete case how you can use this technology to really produce very sharp bounds on estimates of cohomology of jet spaces, exactly of the type needed to solve the Green Griffiths conjecture. So although the Green Griffiths conjecture is not solved, the easiest statement is as follows. Take a projective variety of general type. So a hypersurface and projective space of degree more than dimension plus 2. Take an entire holomorphic curve from C, complex line, into a variety X. Then it should be located in a proper enterprise. So the locus of entire curves, the entire curves cannot be Zariski dense in varieties of general. To prove this, you have to produce a lot of differential equations. You can produce this differential equation by counting growth of sections.
At this point, this can be only done by Morse inequalities. There is some kind of probabilistic computation that requires Morse inequalities. So you cannot do it. So I will try to show you how one uses these estimates.
Excuse me, I would have said for the optimistic conjecture, is there some reason you didn't say that there exists some little h for which it's achieved?
That the theorem is achieved.
I would have said that's even more optimistic, right?
Actually, I saw very, very recently a paper by a Japanese mathematician claiming more, some kind of equality in the case of surfaces. So in the case of surfaces, you have so much more control of the situation that apparently the infimum is probably minimum. I have the paper, so I can show you.
But you think it's probably not true in higher dimensions? I just not know.
Probably not, because for instance, the minimal model program shows that even to reach a model which is a Neff-canonical kernel, you need to perform a lot of flips and flops, and then you don't get a non-singular model and so on. And it makes it unlikely that in higher dimension you will be able to solve things with only smooth objects. So for this reason, probably